Hello, my name is Boris Gromov. I'm a recent PhD graduate at Dallimol Institute for Artificial Intelligence, ICRA, in Lugano, Switzerland. I would like to present our work on pointing gestures and, in particular, their application to 3D control of drones. The general motivation for using pointing gestures to control robots is rather obvious. Pointing is a natural and intuitive interaction modality for humans to use. We master our pointing skills from an early age and use pointing through our lives to refer to places, objects, other people, and even animals. Pointing is a popular choice in human-robot interaction for tasks requiring explicit and precise position information, such as indicating objects to pick or locations for a robot to go. In our work, we model pointing as a 3D ray that originates at the user's head, passes through the index fingertip, and eventually intersects with the intended target. In HRI, this model is known as the head finger pointing model. To implement this model, we use simplified human kinematics, where we assume that the user is standing upright and points with a straight arm. The head and the shoulder are vertically aligned, and the body length parameters are known. We further assume that the dynamic orientation of the pointing arm is known and acquired, for example, with a variable inertia measurement unit placed on the user's wrist. Previously, we have shown that pointing can be an efficient tool for controlling robots on a 2D plane. For example, like in this video for ground robots, or in this video for quadrotors flying at a fixed height. The fundamental challenge of using pointing is that it does not uniquely identify the target location, so in fact it may lie anywhere along the pointing ray. In the case of ground robots, the environment naturally constrains their motion and therefore fully defines the target location as an intersection of the pointing ray with the ground plane. In this work, we consider control of a quadrotor that freely moves in 3D space, where the environment does not feature any of such constraints. To solve this issue, we developed a method that uses virtual surfaces to constrain the 3D position of the robot. Using a set of well-defined user-centric virtual workspace surfaces and switching between them with an additional control input, the user can reach any target location in surrounding 3D space. We considered several options for workspace shapes, namely vertical cylinder, horizontal plane, sphere, and vertical plane. The first three surfaces are a one-parameter family of surfaces. When the user switches the shape, we set the free parameter in such a way that surface passes through the current robot's position. The vertical plane, however, requires to set additional parameter, the vertical orientation. Our goal was to make the interaction process efficient and intuitive for the user. For this reason, we chose to let the user switch only between the first two shapes, so between vertical cylinder and horizontal plane. The vertical cylinder is centered around the user and allows them to control the robot's vertical position without limitations, while never affecting the horizontal distance. We consider this option the safest and the most comfortable to use, and therefore make it default during the interaction. The horizontal plane is set at a fixed height and serves a similar role to the ground plane. It is a natural choice for indicating locations and that allows independent change of the distance between the human and the robot without affecting the robot's vertical position. To prove the viability of our approach, we conducted a user study with 10 subjects, where we compared the performance of the proposed pointing-based interface with a standard joystick. The participants had to fly the drone over a set of randomly given targets using the pointing-based and joystick interfaces. The targets were placed at different heights and represented wireless lights that change their color when the target is cleared. Here is how the experimental session looked like. Note that the user holds the joystick in the other hand to switch between the shapes using the trigger button. To better understand how the system works, let us consider the following animation created from the recorded data that is also was shown in the previous video. Here the tall cylinder represents the user, the short cylinders are the targets, and the little moving ring is the drone that starts at the target marked with an arrow. By default, the system starts with a cylindrical shape. The user lowers the drone, then switches to the planar shape and moves the drone forward, then lowers the drone again with the cylindrical shape. We collected data using the ROSBAC tool from ROS and analyzed it offline. To compare the performance of the two interfaces, we used a relative trajectory length and time to target metrics. This plot shows the evolution of distance to target in time. The first two graphs show how the distance change over time for all users and all segments flown using the joystick and the pointing interface. It gives also a rough idea of the data variance. The third graph compares the means, and we can see that the performance of the two interfaces is very similar. To find exact differences, we further analyzed the relative length of trajectories flown with each interface. Relative trajectory length is a ratio between the length of a segment flown and the length of an ideal straight line trajectory. The closer the relative length to 1, the better the performance. Here we present the results on a 2D plot. The relative length of trajectories flown with the two interfaces define the positions of each dot. The more dots on the right side of the diagonal means the better performance of the pointing interface compared to the joystick. So, according to this plot, we can say that our interface slightly outperforms the conventional joystick control in terms of the trajectory length. We think that the main reason why pointing performed better in terms of trajectory length is because it yields smoother trajectories. In these animations, we can see that trajectory performed with the joystick consists of mostly orthogonal pieces, while segments of the trajectory performed with pointing are more smooth. For further analysis and detailed discussion, please refer to the paper and the supplementary appendix. To summarize, we presented an intuitive interface for controlling a quadrotor in free 3D space using pointing gestures. Although this control mode has only 2 degrees of freedom, it can be efficiently used when combined with dynamic geometrical constraints. We have shown that intersecting a pointing ray with such surfaces allows one to efficiently control the robot in the entire 3D space. Thank you for your attention.